Here's the story everyone's been told about a quantum computer. You've got a maze, a monstrous one, a million twisting corridors, and somewhere deep inside it, one door with the answer behind it. And the quantum computer, so the story goes, splits into a ghostly army of copies and sends one sprinting down every single corridor at once, tries all of them in one blazing instant, and strolls back out with the prize. It's a wonderful story, and it is flatly, completely wrong. That is not what these machines do, and if you carry that picture in your head, you will never understand a single real thing about them. Because the true trick is stranger than the story, and quieter, and so much more beautiful. The true trick is that a quantum computer makes the wrong corridors erase themselves, the way a pair of noise-cancelling headphones reaches out and swallows a sound whole, until there is silence where there was a roar, and leaves only the one right answer behind, ringing like a struck bell.
And that swallowing of the wrong answers, is the single most important idea in this entire course. If you take one thing from all 12 of our evenings, I'd have it be tonight's. Because that myth you described, the army in the maze, is the thing standing between almost everyone and actually getting it. It sounds like magic, and because it sounds like magic, nobody ever asks the next question. But the truth underneath is not magic at all. It's something you've already seen with your own eyes, in a puddle, in a pair of headphones. Tonight I get to show you that the heart of a quantum computer is a thing you've known since you were a child. You just never knew it was the heart of anything.
All right, I want that, but let me hold you to where we've been. We built the qubit, the coin that, while it spins, is genuinely somewhere a coin cannot be. A blend, a direction pointing anywhere on a sphere, with those things you called amplitudes setting the mix. Then entanglement. Two of those coins tied so their fates are one, no message passing between them. Those were the pieces. Tonight feels like the first night we actually do something with them.
That's exactly right. The honest turn in the whole series. Up to now we've been handed the raw materials, these marvelous qubits and this strange glue, entanglement that binds them. But a pile of materials isn't a machine. Hand someone the finest gears and springs ever cut, and they still can't tell the time. You have to act on the pieces, nudge them, turn them, wire them together in an order that means something. Tonight is about the acting. What is a quantum operation? And then the payoff. The thing all that machinery is for. What a gate really is.
So start me where I'm comfortable. My laptop, the ordinary one on my desk, it computes somehow. When people say it's got logic gates inside, millions of them, billions, what is a gate, really? Strip it down for me.
Stripped right down, a gate is the tiniest possible act of reasoning a machine can make. It takes a bit or two in, a bit being just a 0 or a 1, a yes or a no, and hands a bit back out by some flat little rule. Take the one everybody meets first, the AND gate. It swallows two bits and asks one dull question. Were both of you a 1? If so, it hands back a 1, otherwise a 0. That's the whole of it. Stack millions of those, wired one into the next, and out the far end comes a spreadsheet, a video call, a game. All of thinking in a machine is towers of these trivial yes or no rules.
Fine. So a quantum gate is the same kind of thing, a tiny rule, but for qubits instead of bits.
The same spirit, a tiny act, a nudge, but with one deep difference that changes everything, and I want to sneak up on it, because it's gorgeous. Let me ask you something odd about that AND gate first. I put 2 bits in, I get 1 bit out. Now, could you run it backwards? I tell you the answer that came out was a 0. Can you tell me what went in?
No, I can't. A 0 could have come from, let's see, a 0 and a 0, or a 0 and a 1, or a 1 and a 0? 3 different things going in, all giving the same 0 out. So, knowing the answer, I can't walk it back. The information about what went in is just gone.
Gone. And you felt that word land. 2 bits walked in the door, 1 walked out, and a bit's worth of "which was it" got thrown in the bin. Now cast your mind back to our very first evening. Information is physical, the banner of this whole series, and we found this astonishing thing. Erasing information isn't free. Throwing a bit away costs a little heat, a little energy released into the world. It's not bookkeeping, it's physics. It warms the room.
I remember, that was the one that hooked me in the first place, that forgetting a thing costs the universe something real. So you're telling me an ordinary AND gate, every time it fires, is quietly forgetting and quietly warming the room by a hair.
Every single time, billions of little acts of forgetting a second, each paying its tiny tax in heat. And that plants a question that sounds almost philosophical, but turns out to be the key to the quantum door. What if you built a machine that never forgot anything, whose every step you could always run backwards and recover exactly what went in? A reversible machine.
Is that even possible? It sounds like a machine that isn't allowed to make up its mind.
It's not only possible, it's a beautiful little corner of ordinary computing that people worked out long before anyone built a quantum anything. Take the humblest gate of the lot, the NOT gate. It just flips. 1 goes in, 0 comes out. 0 goes in, 1 comes out. Now run that 1 backwards. I tell you a 1 came out. What went in?
A 0. Cleanly, there's only one answer, because NOT doesn't merge anything. It just swaps them, 1 for 1. Nothing gets thrown away, so I can always undo it.
You can always undo it. A perfect little dance step. Forward and back, no partner lost. And here's the thing that ought to raise the hair on your arm. Every operation a quantum computer performs has to be that kind of step. Reversible, no exceptions. It's not a tidiness choice some engineer made. It's forced on us by the deepest law of how quantum things evolve. Down at that level, the universe never forgets. Its bookkeeping is perfect. So every quantum gate is a move you can always run in reverse, landing exactly where you started.
Hold on, that's a strong claim. The universe never forgets at the quantum level? Then why does my coffee forget it was ever hot? Why does anything in my life run one way and not backwards?
A fair objection, and the honest answer is that the forgetting in your kitchen is a crowd effect. The information about that hot coffee isn't destroyed, it's just scattered among unthinkable numbers of jostling particles, far too scrambled ever to gather back. But down at the level of 1 qubit, 1 clean quantum step, the rule holds with full force. Nothing is lost. Every step can be walked back. Gates as rotations.
All right, so a quantum gate has to be a move I can undo. How do I picture one? Give me the mental image.
Go back to the picture we built for the qubit itself, the arrow. We said a qubit is like an arrow that can point anywhere on the surface of a globe. Straight up at the North Pole, let's say that's a clean 0. Straight down at the South Pole, a clean 1. And all the directions in between, pointing at the equator, tilted halfway. Those are the blends, the superpositions, the arrow caught between the 2 poles. Have you got the globe in your head?
I've got it. 0 at the top, 1 at the bottom, everything in between wrapped around the middle.
Then a quantum gate is simply a turn of that arrow, a rotation. You reach in and swing it to point somewhere new, about some axis, through some angle. That's all a gate is. And do you see why that's automatically the reversible, never-forgetting move we needed? Any turn can be unturned. Swing the arrow one way, you can always swing it back. A rotation never crushes 2 directions into one, the way "and" crushed 3 inputs into a single 0. It just points things somewhere else. Nothing lost.
Oh, that's clean. So the NOT gate, in this picture,
Is the simplest turn of all. It's the flip that takes the North Pole to the South Pole. Grab the arrow at the top, swing it a full half turn, and now it's pointing at the bottom. 0 has become 1, 1 has become 0. It's a rotation, and undoing it is just the same flip again. 2 flips and you're home.
good, that I can hold. But a flip just swaps my 2 poles. It doesn't get me anything new. Where do the blends come from? Where's the gate that actually makes a superposition? That takes a plain, boring 0 and turns it into this in-between thing you keep promising me.
Now you're asking for the Stargate, the one that earns its keep in nearly every quantum program ever written. It's got a clumsy name, so I'll nickname it the Splitter. You feed it a clean 0, arrow at the North Pole, and instead of flipping it to the south, the Splitter swings it exactly onto the equator, pointing dead sideways, perfectly balanced between 0 and 1. Measure it now, and it's an honest coin toss. Half the time a 0, half a 1. The Splitter took a certainty and made it a genuine both-at-once blend.
So that's the gate that opens the door to all the quantum weirdness. The one that makes the blend.
That's the one. And it has a property so important, I want you to promise you'll remember it. Run the Splitter twice, feed a clean 0 in, split it to the equator, then split it again. And what do you get back?
Well, following your own rule, everything's got to be reversible. So if I do the same move twice, do I come back to where I started? A clean 0 again?
A clean 0 again, bang on. Split, then split again, and the blend collapses back into the certainty it came from. And that little fact, that splitting twice brings you home, that innocent-looking fact is the seed of the entire magic trick I'm building toward tonight. Because think about what it means. You went from a certain 0 out into a fuzzy both at once, and then back to a certain 0. The fuzz didn't stay fuzzy, it reassembled. Something in that blend remembered how to come back together perfectly.
And I feel like I'm supposed to find that surprising, but let me say why it isn't, and you can tell me what I'm missing. If the Splitter just makes a 50-50 coin, then splitting twice is like flipping a coin, then flipping it again. I just get more randomness. Why does the randomness undo itself instead of piling up?
That is the question. That is the whole ball game, and you just walked us straight to the edge of it. Hold that thought, hold it hard, because answering it is going to crack the entire subject open. But I have to give you one more piece first. One hidden thing about those blends that a coin does not have. And it's the piece that makes all the difference in the world. The thing amplitudes have that coins don't.
Go on, what does the blend have that my coin doesn't?
A coin mid-air, you might say, is half heads, half tails. Some chance of each. And chances, probabilities, are well-behaved things. Always some amount between nothing and everything. You can't have a -1/4 chance of rain. The words don't even mean anything. Probabilities are all positive. They only ever pile up.
Right, a negative chance is gibberish, sure.
But the numbers describing a quantum blend, the amplitudes, setting how much 0 and how much 1 is in the mix, are not ordinary chances. They're richer. And the crucial way, for tonight, an amplitude can be positive or negative. It can carry a sign. You can have a blend that's some 0 and some 1, and another that's some 0 and some -1. Same amounts, one flipped in sign. And here's what'll bend your evening. Those two blends are genuinely, physically different. Not the same state in a different coat.
Wait, but if I just measure them, you told me measuring squares away all the subtlety and hands me a plain 0 or 1. Wouldn't some 1 and some -1 give me the exact same odds? The minus, when I check, would just vanish.
It would. If all you ever did was measure, immediately you would never ever catch the difference between a 1 and a -1 in the blend. The sign hides perfectly from a direct look, which is exactly why it took humanity so long to realize it was there, and why it feels like a cheat when you first hear it. But, and this is the whole but of the night, the sign does not hide from another qubit, or from another gate, or from the blend running into itself. The sign is invisible to measurement, but it is loud and consequential in every step before you measure. It steers where the arrow goes next. It decides whether things build up or cancel out.
Cancel out. There's that word again from your opening, the wrong corridors erasing themselves.
There it is. And now I can finally answer the question you asked me 2 minutes ago. Why splitting twice brings you home instead of piling up randomness. So let's build it, slowly, out of a thing you have absolutely seen. Interference, the whole secret. Picture a still pond. Drop one stone. What happens?
Ripples, rings spreading out from where it went in.
A wave. Crests, the high parts of the water, and troughs, the low parts, marching outward in rings. Now drop 2 stones, a little apart, at the same moment. 2 sets of rings spread out and crash into each other in the middle of the pond. And here's what you see in that crossing region, one of the loveliest sights in all of physics. In some spots, a crest from one stone lands exactly on a crest from the other. 2 highs stacking, and the water leaps up higher than either ripple alone. But in other spots, a crest lands exactly where the other stone sends a trough. A high meets a low. And there,
They'd cancel. The high fills in the low, the water goes flat, still. Like nothing happened at all, even though 2 waves are pouring through that exact spot.
dead flat. Perfectly still water in the middle of 2 roaring sets of ripples, because 2 waves are passing through it, not despite it. That is interference. Overlapping waves don't just muddle into more wave. They add up where they agree and wipe each other out where they disagree. Crest on crest, a bigger crest. Crest on trough, nothing. And you've heard it, not just seen it. It's exactly what noise-cancelling headphones do. They hear the roar of the aeroplane engine and generate the anti-roar. A wave, trough for crest, the opposite of the engines, and the 2 pour into your ear and flatten into silence. Sound plus sound equals quiet. Interference, right against your eardrum.
I love that noise. Plus noise makes silence. It feels illegal. But, okay, pond, headphones, I'm with you. Now bring it home. What has any of this got to do with my qubit and its little arrow?
Everything. Because those amplitudes, those blend numbers with the secret signs, behave exactly like the height of a wave. A positive amplitude is a crest, a negative one a trough. And when a computation can reach the same final answer by more than one route, the amplitudes for those routes don't just sit side by side, they add, wave style. 2 routes both arriving as crests reinforce, and that answer gets louder, more likely. But one route arriving as a crest and the other as a trough.
They cancel. That answer goes flat, silent. It becomes impossible, even though each route on its own was perfectly happy to give it to me.
That answer becomes impossible. And feel how outrageous that is, because a plain probability could never do it. With ordinary chances, more routes to an answer only make it more likely. You pile chance on chance, positive on positive. No path ever undoes another. But with amplitudes and their signs, a second path can reach in and annihilate the first. 2 ways of getting an answer can add up to no way at all. That's the thing classical machines simply do not have. The new verb in the universe. And now you know why splitting twice brings you home.
Okay, let me try it. The first splitter sends the arrow into a blend. Like the two stones, it opens more than one path. The second splitter brings those paths back together, and when they recombine, the signs are arranged so the path leading to 1 cancels. Crest meets trough, it goes silent, and the path leading to 0 reinforces, crest on crest. So I come out certain of 0. The randomness didn't pile up, it interfered itself back into a certainty.
Give yourself a moment. You just derived the beating heart of quantum computing out loud from a pond. That's exactly it. The blend was never a coin flip waiting to happen. It was two waves in one qubit, carrying their secret signs, and the second gate let them crash back together. The wrong answer cancelled itself. The right answer rang out. Split, split, home. It was interference the whole time, wiring it into a machine, the circuit.
Then let me make sure I can see the machine, the actual computer, not just one qubit doing a trick. How do I put these gates together into something that computes?
The picture is beautifully simple, and it demystifies the whole thing. Draw a set of horizontal lines across a page, one for each qubit. Read left to right, and left to right is time, each qubit's life story unfolding. Along those lines you place your gates, little boxes sitting on the wires. Here a splitter, there a flip, here a gate that reaches across two wires at once and ties them together.
The entangling ones, from last time. A gate that acts on two qubits so their fates get bound.
Exactly those. The most famous is a gate where one qubit controls another. If you are a 1, flip your neighbor. If you are a 0, leave it be. Feed that a qubit sitting in a blend, and it spreads the blend across both. And now they're entangled, their stories fused. So, you lay out your wires, sprinkle your gates along them in whatever careful order the problem demands, and that whole sheet of wires and boxes is your quantum program. It's called a circuit. No mystery furnace in the middle, just a recipe. Do this turn, then tie these two together.
And at the far right of the page, the end of time for my qubits?
At the far right, you measure. You finally look, and everything we've suffered through these last few weeks comes due in that instant. Because measuring is brutal, it takes all that gorgeous, subtle, sign-carrying quantum richness and crushes it to a single plain answer. One string of ordinary zeros and ones falls out, and the blend is gone. You get one reading, and which one is a matter of chance, set by the amplitudes you built up by the time you reached the end of the page.
Ah, and that's the catch that's been nagging me this whole series. You keep telling me a qubit holds all this whole arrow, this rich blend, these hidden signs, and then at the very end, I'm only allowed to yank out one measly 0 or 1. It's like being handed a library and permitted to read a single word.
A single word, and you have just put your finger on the central heartbreak and the central discipline of this entire field. You cannot read out the whole blend. Nature will not let you. You put a fortune of quantum information in, you get one thin classical answer out. So the entire art, the whole game, the reason algorithms are hard and precious, is this. You must engineer the amplitudes, all the way along that circuit, so that the one answer you're finally allowed to read is overwhelmingly likely to be the one you actually want.
And the tool for engineering the amplitudes
Is the only tool there is. Interference. You arrange the whole circuit so that by the end, the amplitudes for every wrong answer have crashed trough on crest and cancelled towards silence, while the right answer has built up crest on crest until it towers over everything else. Then you measure, and the answer overwhelmingly likely to fall out is the right one. The computation isn't a search, it's a sculpting. You start with a block where every answer is equally possible and chip away, with interference, everything that isn't the answer, until only the answer is left standing.
Sculpt away everything that isn't the statue. Okay, that's a completely different picture from the army in the maze. Nobody's running down every corridor. You're shaping a wave until only one outcome survives.
And now you're ready. Finally, properly ready. For the little puzzle that first showed the world this could actually be done. The first time anyone proved, on paper, that a quantum machine could do a thing no ordinary machine can. It's a toy. It's almost silly how small it is. But it was the first crack of dawn, and every giant thing that came after is just this same trick, blown up to a monstrous scale. The Deutsch puzzle. The first real aha.
I've been waiting for the payoff all night. Give me the toy.
A physicist named David Deutsch dreamed it up, so we'll wear his name on it. The setup's genuinely simple. Imagine a little sealed box, a mystery machine with one job. You feed it a single bit, a 0 or a 1, and it hands you back a single bit. One bit in, one bit out. But you can't see inside. You don't know its rule. It's sealed.
A mystery function. I put in a 0, it gives me something. I put in a 1, it gives me something. And I can't see how it decides.
Right. Now how many rules could possibly be hiding in that box? Let's count. It has to say what to do with a 0 and what to do with a 1. And there turn out to be exactly 4. 1. Always spit out a 0, whatever comes in. 2. Always spit out a 1. 3. Echo the input back. 0 gives 0, 1 gives 1. 4. Flip it. 0 gives 1, 1 gives 0. 4 boxes. That's every rule there is.
4. Okay, and I'm guessing you're about to sort those 4 into 2 families.
You read my mind. The first 2, always 0 and always 1, don't care about the input. They give the same answer both times. Call those the constant boxes. The other 2, echo it and flip it, give different answers for the 2 inputs. Call those the balanced boxes. Even-handed, one of each.
Constant, same answer both times. Balanced, different answers. 2 families of 2.
And here's the only question I'll ask about your sealed box. Not what it does to a 0 specifically, not what it does to a 1. Just this. Is it a constant box or a balanced one? Same both times or different? One bit of an answer, but a bit about the box's whole character, not about any single input.
All right, and now I want to solve it the boring way first, so I know what we're beating. I've got the sealed box. I want to know, constant or balanced. What do? I run it.
You run it. Feed it a 0. Out comes, let's say a 0. Now, have you learned the answer? Do you know yet if the box is constant or balanced?
No, a 0 came out, but that's consistent with 2 different boxes. The always 0 box, constant, or the echo it box, which is balanced but also gives 0 for 0. One run leaves me stuck between a constant box and a balanced one. I genuinely can't tell them apart yet.
You cannot. One look is useless. It never distinguishes the families. So what must you do?
I've got to run it again. Feed it a 1 this time and compare the 2 answers. If they match, same both times, it's constant. If they differ, it's balanced. So I need 2 runs. 2 questions to the box. No way around it.
No way around it, classically. That's the key. With any ordinary logic, you're stuck asking the box twice. One query tells you nothing about its character. You need a second to compare against. 2 peaks minimum for that 1 bit of personality. Now, hold your breath, here comes the sunrise. Deutsch showed that with a quantum box, you can learn the answer. Constant or balanced, for certain, no luck, by consulting it just once. A single query. Fewer than the laws of ordinary logic permit. That gap, 1 instead of 2 was the first crack of light. The first proof that this stuff wins.
One query. But hang on, let me object, because it sounds like a cheat. You told me a qubit blend gives me only one answer when I measure it. So even if I somehow feed the box a blend of 0 and 1 at once, and it does its thing to both at once, I still only get to read one bit at the end. I still can't see both answers. So how does one query tell me anything 2 didn't?
That is the perfect objection. That is the objection, and the fact that you raised it means you've actually understood the trap everyone falls into. You are completely right. Feeding the box a blend does not let you read out both answers. If that's all the trick were, run it on a superposition and peek at both. It would be a swindle, and nature would slam the door, because you only ever get one reading. So that is not the trick. Watch what the trick actually is, because it's the whole lesson of the knight wearing its finest clothes.
I'm watching.
You do not try to learn what the box does to a 0 or to a 1. You give up on both. You accept you can never have them both. Instead, you build a little circuit, a splitter, then the box, then a second splitter, that asks a completely different question. Are the 2 answers the same or different? Not, what are they? Only, do they agree or disagree? And notice, same or different is precisely constant or balanced. That one comparison between the 2 hidden answers is the entire thing you wanted. And interference can hand you the relationship between 2 answers, even though it can never hand you the answers themselves.
So I'm not extracting 2 facts and comparing them. I'm asking the wave itself to do the comparison for me, and only report the verdict.
Exactly that. Let me walk the circuit so you can see the waves crash. First splitter. It takes your qubit and opens it into a blend. Sends it, in effect, down 2 paths at once, the 0 path and the 1 path, like the pond's 2 stones. Then both paths pass through the mystery box together. And here's the sly bit, the part that took genius to see. You wire it so that the box, instead of scribbling its answer down somewhere you'd have to read, stamps its answer onto the sign of the wave, onto the crest or trough of each path. The box's output doesn't come out as a number you read, it comes out as a plus or a minus riding on each path.
So the answer to 0 gives what becomes a sign on the 0 path, and 1 gives what becomes a sign on the 1 path. The box's replies are hidden in the crests and troughs now, not in anything I can read directly.
Beautifully put. And now the second splitter does its job. It crashes the 2 paths back together. And whether they recombine into a clean, ringing 0 or a clean, ringing 1 depends entirely on whether those 2 signs agreed or clashed. If the box was constant, same answer both times, both paths got the same sign. Crest meets crest. They reinforce and send the arrow cleanly to one pole. You read a 0, dead certain. But if the box was balanced, different answers, the paths got opposite signs. Crest meets trough. They interfere the other way and send the arrow to the other pole. You read a 1, dead certain.
So I look at that final single bit, and if it's a 0, the box was constant, and if it's a 1, the box was balanced. 1 reading, 1 query to the box. And it's not a coin toss, it comes out certain every time, because the interference is total. The waves either fully reinforce or fully cancel.
For certain, every time. No luck. The wrong verdict cancelled itself, went true on crest to silence, and the right verdict rang out alone, and you read it. 1 question to the box, and you learned its whole character. A thing that ordinary logic swears is impossible in fewer than 2.
And the reason it doesn't break your "you only get 1 bit" rule is that the 1 bit I pull out isn't what the box does to a 0. It's the comparison, the relationship, same or different. I spent my single precious reading on the one question whose answer I actually wanted. Instead of wasting it trying to learn a raw value, I'd only have had to compare anyway.
That's the whole song. You didn't compute more. You computed smarter. You never learned two things and compared them. You built a machine where the comparison happens in the interference itself, and only the verdict survives to be read. The box was asked one question about all its inputs at once. Taken all together, are you steady or even-handed? And interference converted that global question into a single certain bit. That, right there, is the first real aha of quantum computing. Small as a mouse, and the seed of everything. Why this tiny thing is the whole key.
I have to be honest with you, though, and you'd want me to be. Saving one query on a sealed box, asking once instead of twice, that's the entire miracle. It feels almost like a letdown after the maze and the bells. Who cares about one query?
You're supposed to feel that. We've spent this whole season refusing to oversell. On its own, the Deutsch box is a party trick. Nobody's getting rich saving a single query. But it's like standing over the first tiny flame a human ever coaxed from 2 sticks and sniffing, "That's it? I can't even cook on that." No, you can't. But you're not looking at a campfire. You're looking at the principle of fire, and the principle is what eventually forges steel and flies to the moon.
So it's not the size of the win, it's that a win of this kind was shown to be possible at all.
That's the whole of it. For the first time, someone proved, airtight on paper, that by loading a question into a blend and letting the answers interfere, you could learn something about all the inputs together in fewer steps than checking them one by one could ever allow. Once you know that door opens, the only question left is how big the room is. And it's enormous. Every famous quantum algorithm, the ones we'll spend next time on, the ones that rattled the world, is this same splitter box, splitter heartbeat, scaled up from a box with 4 possible rules to a haystack with more hiding places than there are atoms in a mountain. You spread a question across a colossal blend, compute once so the answer gets stamped onto the signs of the waves, and let interference cancel the unthinkable multitude of wrong answers down to silence, until the hidden pattern you are hunting rings out where you can read it.
And I want to catch the honest caveat before you say it, because you always make me carry one. This erasing of wrong answers, it can't be free. It can't work on just any question.
There it is, right on cue. And it's the most important sentence in the whole enterprise. Interference is choosy. To make the wrong answers cancel and the right one reinforce, the problem has to have a hidden structure. A pattern a clever circuit can grab and turn into agreeing and disagreeing waves. When it's there, factoring a number, hunting a needle, mimicking a molecule, the cancellation is spectacular and quantum wins big. But hand it a shapeless heap with no pattern, and there's nothing for the waves to grab. Nothing lines up to cancel, and a quantum computer plods along no better than the machine on your desk. It is not a magic box that speeds up everything. It's a wave sculptor, and it can only carve where the marble has a grain.
So the maze story wasn't just wrong about the mechanism, running down every corridor. It was wrong about the promise. These machines don't win at everything. They win where interference has something to bite on.
They win where the marble has a grain. And we'll test that hard a few evenings from now, when we reckon honestly with what these machines cannot do. But I don't want the caveat to be the note you leave on, because tonight is a night of arrival. For weeks I've handed you strange, disconnected marvels, the coin that spins into a blend, the 2 coins tied across the void, and asked you to trust they'd add up. Tonight they added up. This is the engine. Turn the arrows with gates, wire the gates into a circuit, then let the amplitudes with their secret signs interfere, so the wrong answers wipe themselves out and the right one is left ringing.
And it circles right back to the very first thing you ever told me. Information is physical. Because interference here isn't a metaphor. The information in that machine is literally riding on something wave-shaped, with real crests and troughs and signs, and it can cancel itself into silence the way sound cancels sound. It behaves like a physical wave because, at bottom, that's what it is.
That's the thread, and you've held it since our first night. Information is physical, and because it's physical, it can do the one thing no paper and pencil information ever could: interfere with itself, so the wrong answers erase themselves. That's not a trick of the machine. It's a property of reality we've merely learned to put to work.
So the next time somebody tells me a quantum computer tries every answer at once,
You'll know the truer, stranger thing. It doesn't try every answer. It makes the wrong ones disappear. It's not an army sprinting down every corridor of the maze. It's a single wave, poured in, arranged so every path to a dead end cancels against every other, until the only place the wave hasn't erased itself is the doorway you are hunting for. It doesn't search the maze. It makes the maze sing and listens for the one note left standing.
I came in tonight thinking a quantum computer was a faster kind of guessing, brute forcing everything at once. And I'm leaving with something almost musical instead. Waves cancelling waves until an answer rings. That's the click, isn't it?
That's the click. And now that you can hear it, you're ready for the loud part. Next time we take this one small, singing note, the toy box that saved a single query, and turn the volume all the way up, because someone aimed this exact trick at the codes that guard every secret on Earth. And when they did the arithmetic, the whole world went quiet for a moment. But that's a story for next time.
The wrong answers erase themselves, and the right one rings. I'll be hearing that in everything now. Good night.